Hey guys, welcome back. Today's video is an important one. We'll define stationarity and how to address it using control charts. This lets us build up to white noise and a random walk in the next video. Alright, so let's talk about a core concept in time series analysis, stationarity. In essence, stationarity is a property of a time series that exhibits constant mean and constant variance over time. It's a bit more nuanced than that though, as we'll see later on. These properties make it easier to model data and make predictions. Looking at this time series, do you think it's stationary? We can immediately spot several patterns. First, there's an increasing trend in t. As t increases, y of t also increases. There's also some sort of periodic behavior, but it doesn't seem to be consistent for all t. And finally, the noise seems to be increasing as t increases. If we look at higher values of t, the up and down movement becomes more erratic. Going off our general definition of constant mean and variance, we can confidently say that this series is non-stationary. So what if we isolated these issues one by one to weed out the non-stationary parts? First, we'll remove the periodic pattern. Notice how the up and down movement is now gone. Now, let's get rid of the increasing trend so that the mean is constant, so that we're just left with the noise. The variance still seems to be increasing over time, so we'll make the noise constant over time. And voila! We now have a stationary series. So now that we've seen what a stationary series looks like, how do we formalize the definition? Stationarity comes in two main flavors, weak and strong. Weak stationarity is the more common definition in use in practice, so we'll start with that. A time series is weakly stationary if it meets two specific conditions. First, the mean must be constant. It doesn't drift up or down depending on when you look at it. And second, the covariance between 2 points, ys and yt, depends only on the lag between them. It is not dependent on the actual time they occurred. An implication of the second condition is constant variance for any specific point in time. This is also known as homoscedasticity. What does constant mean look like? If we plotted the average value over time, it would just be a flat horizontal line. It's pretty straightforward. Now, what does it mean for covariance to depend only on the lag? Imagine we pick 2 points separated by a specific time distance, or lag. Let's say 2 steps apart. If the series is weakly stationary, the covariance of these points should depend only on that lag distance, not on when we look. Whether we are at time 1 or time 6, if the lag is the same, the covariance structure is consistent. Finally, imagine 2 horizontal bands around your data. If the height of those bands stays roughly the same over time, you have constant variance. The spread is constant. This follows from the second condition. If s equals t, then the covariance is just the variance of yt, hence the same constant variance for any t. The opposite is heteroscedasticity. This is when the data fans out, or the spread changes over time. That is not stationary. The second type of stationarity is strong or strict stationarity. The first two conditions are the same as weak stationarity. The mean must be constant over time, and the covariance between 2 points depends only on the time difference between them. For a series to be strongly stationary, a third condition must be met. The entire distribution, not just the mean and variance, must remain constant over time. It's a much tougher condition to meet, especially in real-world scenarios. In most cases, weak stationarity is sufficient. Now that we know what stationarity is, how do we address it? To do this, we use control charts. These are visual checks for a time series, y of t. We can denote the mean as y bar and the standard deviation as s of y. To use a control chart, we first need to set up boundaries, an upper control limit, or UCL, and a lower control limit, LCL. The source material uses 3 standard deviations as an example, so we'll go with that. This range can vary depending on our data and desired level of confidence. Consider this chart. We have our reference lines. These help us spot violations of stationarity. Here is a nice, well-behaved data set. Look at that. All the points are staying safely inside the lines. These points aren't violating anything. But watch point 19. Oh crap, violation. How naughty. It decided to jump over the UCL. Since it's outside the limits, this makes it so the entire series is not stationary. Way to go, point 19. Let's finish this section off by quickly going over the different types of control charts. The source material doesn't go into detail or provide any visuals, so I created these from external sources. I think it helps with visualizing the concepts, but you're probably also not going to need to know this much detail for the exam. A retrospective chart uses all available data points to calculate the mean and limits. We are looking back at the entire history to judge stability. Next is the prospective chart. Here, we establish our HCL and LCL using only a baseline set of historical data, or Phase 1. Then, we project these limits forward to monitor new incoming data in Phase 2. The X-bar chart tracks the stability of the mean. Instead of plotting individual raw data, we take a subgroup, average them together, and plot that single mean value. Note that the subgroup is a collection of data points grouped by some quality characteristic. The x-axis is no longer the time index, but the subgroup index. This allows us to observe patterns in the central tendency rather than individual points in time. The R chart tracks variability by plotting the range. For each subgroup, we look at the difference between the maximum and minimum values. We take that specific distance and plot it as a single data point. Similar to the X-bar chart, the x-axis is no longer the time index, but the subgroup. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.